Sir, I'll do the introduction.
Okay.
Good evening, everyone. Welcome to the first event of IEEE GSET Signal Processing Society Student Branch chapter of the calendar year 2022. Today, we will be having a webinar on the topic Fundamentals of Radar Signal Processing. Our speaker for the event is Professor B. Harikumar, Sir, Professor and Dean Academics, Geetanjali College of Engineering and Technology. Sir completed his BE in Electronics and Communication Engineering from Andhra University and further pursued masters in Osmania University. Sir has an enormous teaching experience of 36 years and has held various administrative positions such as HOD, Associate Dean, and Dean. His research areas of interest include microwaves, antennas, and global positioning system. He has published 15 research papers in various international and national journals and presented about 10 papers at various prestigious conferences. He is known more for his expertise in teaching electromagnetic theory, antennas, and microwave courses for the GATE and IES exams. It's a pleasure having you with us today, sir. Now I request sir to take over the session.
Okay. Thank you for your good words about me. My dear students and faculty members, a very good evening to all of you. In today's webinar, so I'm going to discuss about the working principle of fundamental radar, and then we are going to discuss about various types of radars. And in particular, I'm going to concentrate more on the working principle of pulse radar, CW radar, and FM CW radar. In fact, depending upon the application, we've got different types of radars. So pulse radar, mainly to measure the distance from the radar to the particular target. The target can be a flight, okay, or it can be any object, okay, like missile. And then we've got continuous wave radar, CW radar, which is mainly to measure the relative velocity of the target with respect to radar. It is something like suppose an aircraft is moving with certain velocity and you would like to find out with what velocity it is traveling. So for that we use CW radar. By using FM CW radar, both distance and velocity both can be measured. And in fact, what happens is by using a pulse radar, it is not possible to measure the velocity, and CW radar can't measure the range, distance to the target. But by using FM CW radar, both distance and velocity can be obtained. Similarly, we got MTA radar mainly to identify the moving targets in the presence of clutter. Clutter means stationary targets which are undesirable targets. And then we got tracking radar. Tracking radar basically supplies a continuous information on one or more number of targets. That information could be a continuous information about the range of the target, its elevation angle, azimuth angle, velocity, etc. Okay. In today's webinar, we're going to concentrate on the pulse radar, CW radar, and FM CW radar. And if you look at the applications of radar, basically we've got civil applications as well as military applications. A radar can be used as a navigational aid on ground or sea. In fact, in the airports, currently we are using instrument landing system. So during the nights also, by using this instrument landing system, in fact, flights are able to land very safely. Okay. Similarly, radar altimeters, basically to measure the height of a plane, we use our buildings also. We use radar altimeters. Similarly, police radars, probably you might have seen that whenever there is a speeding vehicle, and suppose if the maximum velocity that is permissible is let us 50 kilometers per hour. If a car exceeds that limit, immediately traffic police they will catch hold of that car. Okay, and how they measure the velocity using CW radar. Okay, so that is one of the applications. Similarly, the cricket ball. Probably most of you might have seen that once the ball is delivered, immediately within no time you will get the speed of the ball, 150 kilometers per hour. That is also by using the CW radar concept. So apart from the civil applications, we got so many military applications also. When it comes to military applications, detection and ranging of enemy targets, even during the night times also, and directing the guiding missiles, and then whenever it is required, we can bomb the ships, aircrafts, etc. by using radars. So these are the various applications. In almost all the radars, the principle is we are going to transmit a signal towards the target, and then there the signal is encountered by the target, and a part of the signal will be reflecting back. See, in radar terminology, the object which we need to detect is known as a target. So it is something, and suppose you are looking for an aircraft. So here the target is aircraft. When you are looking for a missile, so here the target is a missile. The object which we need to obtain or locate is known as a target. Similarly, the distance from the radar to the target. Okay, in radar terminology, that distance is known as a range. And then the echo signal means so once a signal goes to the target, there it gets intercepted by the target, and it will be reflected back. Only a part of the signal will be reflecting back. Okay, and that reflected signal is known as the echo signal. Echo signal is a signal that reflects back to the radar. Okay, so that actually that echo signal will be processed suitably to determine the velocity of the target, to determine the range of the target, to determine the direction of the target. Various things can be obtained by processing the echo signal. And then the clutter means unwanted stationary targets. It is something, suppose you are looking for an aircraft. So once the signal is radiated towards the target, that signal, apart from going to the desirable target, it also goes to nearby trees, buildings, etc. So these are not actually which we are looking for. So these are undesirable targets. In radar terminology, we call them as a clutter. Clutter means stationary, undesirable targets. Okay. So now, if you look at the pulse radar principle, now in this diagram, you can see that a pulse is transmitted. A pulse of energy is transmitted towards the target. So here the target is aircraft. So the signal travels towards the aircraft. There it gets intercepted, and a part of the signal will be reflecting back. Okay. Let me show you one video when basically you can see how it is happening. Now you can see that. So here this is the transmitting antenna. It is radiating a pulse of energy, and this blue dot is the target. So the signal is reaching the blue dot, the target, and then a part of the signal is reflecting back. Okay. Uh, the blue one is the transmitted signal, and then of course the green one. One is the transmitted signal, the other is the reflected signal. Okay. So what we do is at what time we are transmitting this pulse of energy, okay, and at what time we are receiving the corresponding echo pulse. So that once we find out the time taken for the pulse to go to the target and then back to the radar, because it is basically electromagnetic wave, it travels with velocity equal to light velocity. Okay, so once again, let me come back here. So if the distance from the radar to the target is r, the range is r. So during its two transmission, that means when it travels from the radar to the target, it travels a distance of r. Then once it reflects back, it has to travel back from the target to the radar. It covers another distance of r. So in all, it travels a distance of 2r. With what velocity? With the velocity equal to light velocity c. So 2r is equal to c into tr. What is tr? Tr is the time taken for the pulse to go to the target and then back to the radar. So what we need to do is we need to measure the value of tr, the time taken for the pulse to go to the target and then back to the radar. If we can measure that, we can find out the range. Okay. For example, at time t is equal to 0, I'm transmitting a pulse. Okay, that is there is a target A. The corresponding echo pulse is received at this instant of time. So what we do is we find out how much time is elapsed between transmission and reception of the pulse. Let me show you another example so that you can understand in a better way. For example, at time t is equal to 0, I am transmitting a first pulse. Okay. Assume that for every 1 millisecond, I am transmitting a pulse at 1 millisecond, at 2 milliseconds, at 3 milliseconds. Okay. So this 1 millisecond is what is known as the pulse repetition time. Pulse repetition time is 1 millisecond. What is the pulse repetition frequency? 1 by 1 millisecond. So that is equal to 1 kilohertz. So pulse repetition frequency is 1 kilohertz, or actually in terms of pulse repetition time, it is 1 millisecond. Meaning that for every 1 millisecond, I am transmitting a pulse. Okay. For example, you have a target at a distance of 100 kilometers. For example, you have a target at a distance of 100 kilometers. How much it takes, how much time it takes to go to the target, okay, which is at a distance of 100 kilometers, and then come back. The same equation, 2r is equal to c into tr. So 2 into r is 100 kilometers, 100 into 10.3 by c, 3 into 10 to the power of 8. So 0.667 milliseconds. So the time taken for the pulse to go to the target, okay, which is at a distance of 100 kilometers, and then come back to the radar is 0.667 milliseconds. So if we come back here, at time t is equal to 0, I am transmitting a pulse. So when can I expect the corresponding echo pulse? 0.667 milliseconds. Okay. Similarly, at 1 milliseconds, I am transmitting another pulse. So this pulse also has to travel a distance of 100 kilometers. It also takes a same time interval of 0.667 milliseconds. So at what time I will be receiving the corresponding echo pulse? 1 plus 0.667. So 1.667 milliseconds, I am receiving the corresponding echo pulse. Like that, the pulse which is transmitted at 2 milliseconds, the corresponding echo pulse is 2.667. It will be received. So at any instant of time, we observe only one sweep at a time. One sweep means, for example, this is the second sweep. Okay, this is the first sweep. This is the first sweep. Sweep means basically once you transmit a pulse, before you transmit the next pulse, what all the echo signal that you receive is known as one sweep. For example, this is the first sweep. At time t is equal to 0, I have transmitted the first pulse. Before I transmit the second pulse at time t is equal to 1 millisecond, what all the signal that I am receiving, okay, that will record one sweep. So I am receiving a echo pulse at 0.667. So what I do is I am going to subtract 0.667 minus 0, that is 0.667. TR is equal to 0.667. Similarly, 1.667, the second sweep, suppose the second sweep is available to you. Then 1.667 minus 1 millisecond. Once again, you get 0.667. So once you have the value of TR, you will be able to find out the range. So C into 0.667 divided by 2, that gives you the range. Now the range is going to be 100 kilometers. Okay. So this is the simple principle of a pulse radar. Now the point is, at what frequency I will be able to, I can transmit the pulses. Here actually, for every 1 millisecond, I am transmitting a pulse. That means the pulse repetition frequency is 1 kilohertz. Okay. Why can't it be 0.5 milliseconds? Can I afford to transmit a pulse for every 0.5 milliseconds? Okay. What is the basis for, in fact, fixing the pulse repetition time? Is there any criteria? Okay. For that also, let me tell you a simple example. Okay. For example, you have got another target, let us say target B, which is at a distance of 200 kilometers. Target gave us at a distance of 100 kilometers. For the TR is 0.667 milliseconds. Suppose I got another target 200 kilometers at a distance of 200 kilometers. Let me find out what is TR. Is 1.33 milliseconds. So the pulse takes a time of 1.33 milliseconds to go to the target B and then come back. So at time t is equal to 0, if I transmit the first pulse, when do I receive the corresponding echo pulse? 1.33 milliseconds. Okay. At time t is equal to 1 millisecond, I am transmitting the pulse. This pulse also has to go to the target B, which is at a distance of 200 kilometers. It takes the same time interval of 1.33 milliseconds. So when can I expect the corresponding echo pulse? 1 millisecond plus 1.33, 2.33 milliseconds. Okay, like that. Now, as I already told you, at any instant of time, I will be able to observe only one sweep. So this is, for example, you are observing the second sweep. This is what you are going to observe on a scope. A scope basically provides the amplitude of the echo signal. Okay. So when you look at this second sweep, what happens? Normally, we assume that B is the echo pulse received at from target B is 1.33. So 1.33 minus 1. We take TR as 0.33 milliseconds instead of 1.33. Okay. So accordingly, the range that we measure is not going to be correct. I hope you have understood this point. Because at any instant of time, we can observe only one sweep at a time. So this is what it appears on the screen. So we assume that this is the time at 1.33 milliseconds I have received the echo pulse, and we assume that it is due to the pulse that is transmitted time t is equal to 1 millisecond. But it is actually the pulse which is transmitted t is equal to 0 milliseconds. But nobody is going to say that it is the echo pulse received due to the first transmitted pulse. So by all means, we assume that this echo pulse received at 1.33 milliseconds is due to the pulse that we have transmitted 1 millisecond. So we take TR as 1.33 minus 1, that is 0.33 milliseconds, and accordingly we are going to measure. So CTR by 2, C is 3 into 10 to the power of 8, TR is 0.33 milliseconds. So we get 15 kilometers, but the actual distance is 200 kilometers. So the rate at which we are transmitting the pulses, okay, is something related to the maximum range, okay, that can be measured. I hope you have understood this point. Okay, so now can you please tell me what is the maximum value of TR that is allowed? TR of 0.667 milliseconds is allowed. Without any ambiguity, you are able to measure. But when it comes to TR of 1.33 milliseconds, there is ambiguity. What is the reason? By the time we are receiving the echo pulse, we have transmitted the second pulse also. That's why there is an ambiguity. So we are not sure whether this echo pulse received at 1.33 milliseconds is due to the first pulse that is transmitted at time t is equal to 0, or the second pulse that is transmitted at time t is equal to 1 milliseconds. So until that means before we transmit the second pulse, if we receive the corresponding echo pulse, then we are certain that it is due to the pulse that is transmitted at time t is equal to 0. That means what is the maximum value of TR that is allowed? 1 millisecond. Suppose I am receiving the echo pulse here, okay, just before the transmission of the second pulse. Okay, that means TR is 1 milliseconds. Okay, so when TR is equal to T, pulse repetition time, until that point of time, there is no ambiguity in the measurement of waves. So once TR is greater than 1 millisecond, greater than T, then there is ambiguity in the measurement of range. We are not sure whether this pulse is due to the echo pulse received is due to the first pulse transmitted or the second pulse transmitted. So what is the maximum value of TR that is allowed? TR is equal to T, that is 1 milliseconds in this case. So what is the maximum unambiguous range that can be measured. What is the maximum unambiguous range? What is the maximum unambiguous range? It is 150 kilometers. C into TR by 2. So TR is equal to T, that is 1 millisecond. So when you keep on transmitting the pulses, okay, when you keep on transmitting the pulses, for every 1 millisecond, one pulse at a time, actually for every 1 millisecond, what is the maximum range that can be measured? It is only 150 kilometers. That's why target A, which is at a distance of 100 kilometers, can be tracked without any ambiguity, can be obtained. The range of the target can be obtained without any ambiguity. But for the target which is at a distance of 200 kilometers, you are not able to measure the range without any ambiguity. Okay. So the maximum range, unambiguous range is C by 2FP or C TR by 2 or CT by 2. CT by 2 because T is equal to 1 by FP. Now, can you please tell me, suppose you got a target B which is at a distance of 200 kilometers. Okay. What should we do if you want to measure the range of target B which is at a distance of 200 kilometers without any ambiguity? Can anyone answer this one? Anyone? See, when you are transmitting the pulses for every 1 millisecond, the maximum range that can be measured is 150 kilometers, CT by 2. Okay. But for targets having range more than 150 kilometers, for example, target B, which is at a distance of 200 kilometers, as it is, when you keep on transmitting the pulses for every 1 millisecond, it is not possible to measure the range without an ambiguity. So what should we do? What is the parameter that we need to change so that we can measure the range of target B without any ambiguity? What is it we have to do? No idea.
Pulse repetition must be at 2 milliseconds, sir.
Yeah, need not be exactly 2 milliseconds, but pulse repetition time has to be increased. Okay, as you have said, now I am transmitting pulses for every 2 milliseconds. At time t is equal to 0, I am transmitting the first pulse. Second pulse I am transmitting at 2 milliseconds. Okay, third pulse at 4 milliseconds. Okay, so now the pulse repetition time is 2 milliseconds. Pulse repetition frequency is reduced. Now what happens? This won't be there. Is it not? This won't be there. At time t is equal to 0, I am transmitting the first pulse. This pulse has to cover a distance of 200 kilometers. So it takes a time of 1.33 milliseconds to go to the target and then come back to the radar. Okay. And we are transmitting the second pulse only at time t is equal to 2 milliseconds. So before we transmit the second pulse, we are able to receive the echo pulse corresponding to the first transmitted pulse. There is no ambiguity. So 1.33 minus 0. So what is TR? 1.33. So very happily we can measure the range. Okay. Okay. Next. Now these are the radar frequencies. Most of the radars operate between 200 megahertz to 300 gigahertz. Okay. But of course, there is no hard and fast rule that only between these two regions radars need to operate. Okay. Now, in the example that we have discussed just now, if the pulse distribution time is, let us say, 1 millisecond, okay, the maximum range that can be measured is only 150 kilometers. For a target like target B, which is at a distance of 200 kilometers, okay, we are receiving the first echo pulse after the transmission of the second pulse. Okay, so echoes that arrive after the transmission of the next pulse, second pulse, is called second time around echoes. Okay, similarly, suppose if the distance is more 400 kilometers, then what is going to happen at time t is equal to 0? Suppose if you transmit the first pulse, the corresponding echo pulse might be received after the transmission of two pulses. This is known as the third time around echo. In general, it is called multiple time around echoes. Okay. So before we design a pulse radar, we need to fix the pulse distribution time or pulse distribution frequency. So how do you design that? We must have a rough estimation of the distance, the approximate distance at which the target is expected. Say I'm looking for a target, let us say, of 100 kilometers. Okay, the approximate distance of the target which I'm looking is 100 kilometers. Then what I have to do is, to be on a safe side, maximum range that can be measured is, let us say, 150 kilometers. Accordingly, I'm going to fix the pulse distribution time as 1 millisecond, pulse distribution frequency of 1 kilohertz. So one should have a knowledge about the maximum range at which the target is expected. Accordingly, we are going to design the pulse radar. That means design means only pulse distribution frequency or pulse distribution time, choosing the values. Okay, next. Now this is the pulse radar block diagram. A general block diagram of radar also, the same thing can be shown. So here pulse means it is not actually the pulse that we use in IC applications. It's not like that. Basically, you have got a transmitter. The transmitter transmits the high frequency signals, hundreds of megahertz or gigahertz. So what we do is the transmitter is made on and off by the pulse modulator. Okay. So during the on period, what happens? You will have the pulses. Pulses means electromagnetic wave will be there. Something like that. Let me show you here. See, this is the output of the transmitter. So this is the output of the transmitter. So it's a high frequency wave, something like this. Okay. This is a transmitter output. Only a certain period, let's say this is the transmitter is made on. So we'll have the oscillations. And during the remaining period, the transmitter is made off. Okay. Once again, the transmitter is made on. So we'll have the electromagnetic wave transmitted only during this period. So this can be treated as one pulse. So this is T on, this is T off, once again T on, this is T off. Okay. We call this as a pulse. Okay. In fact, normally this pulse width is represented with the tau. Okay. T on plus T off. This is the time period. Okay. Tau divided by K is known as a duty cycle. It's known as the pulse width divided by pulse repetition time. Okay, is known as the duty cycle. So I hope you understood this. So transmitter transmits a continuous wave signal of high frequency signal. Okay, and this transmitter is made on during a certain period of time, tau seconds, and then off. Once again, it will be made on. So each one can be treated as a pulse. Next, particularly in a pulse radar, the same antenna can be used for transmission as well as for reception. Because only during the on period, during the tau seconds, we need the services of a transmitting antenna. And during the remaining period T off, the same antenna can be used as a receiving antenna. Is it? Once again, for the next pulse, for the next tau seconds, the transmitting antenna, the antenna can be used as a transmitting antenna. After that, the same antenna can be used as a receiving antenna. Okay. So if you want to use a single antenna, both for transmission as well as for reception, okay, we use a duplexer. Duplexer basically consists of two gas discharge devices, okay, TR and ATR, transmit receive, anti-transmit receive. The function of TR is to protect the receiver during the transmission period, because basically the strength of the transmitted signal will be several megawatts. Okay, hundreds of kilowatts. Typical value is 1 megawatt of power. Okay, that pulse. Okay, whatever energy that we are transmitting in the form of a pulse, the peak power will be 1 megawatt of power. Suppose if there is any leakage of the signal to the receiver circuit, so this is the receiver circuit. Receiver circuit is very sensitive. It can't handle that hundreds of kilowatts or a few megawatts of power. Any leakage of signal, okay, transmitted signal into the receiver circuit, the whole receiver circuit will be burned. It can handle only microwatts or few milliwatts of signal, the receiver circuit. So we need to protect the receiver circuit from the high powers of transmitted signal. So that is one function of the duplexer that is done by transmit receive. And then the other function is ATR, anti-transmit receive. So once the echo signal is received, the echo signal should not be directed towards the transmitter. The echo signal should be directed towards the receiver circuit, so that echo signal will be processed to determine various parameters like range, etc. Okay, so that is another function of a duplexer that is done by ATR. So ATR, what is the ATR function? To direct the echo signal to the receiver circuit, not to the transmitter circuit. What is the function of TR? TR protects the receiver circuit during the transmission time. That means during the tau seconds of time, okay, receiver needs to be protected from the high powers of the transmitted signal. That is the function of a TR. Next, the first block is the low noise RF amplifier. You have any idea of a low noise RF amplifier? Any idea? Why actually this low noise RF amplifier is used?
Low
Because
noise frequencies are attenuated.
low noise,
I mean, echo signal noise will be eliminated.
echo signal noise will be eliminated. Yes. Basically, the echo signal consists of, apart from the desired signal, okay, it is also accompanied by a noise signal, because the signal has to cover a few hundreds of kilometers sometimes, or at least a few kilometers. So during its to and fro transmission, noise gets added. Okay, and the strength of the echo signal is also, sometimes it is of the order of 10 to the power of minus 18 times that of the transmitted signal. See, the strength of the echo signal is so low that sometimes it could be as low as 10 to the power of minus 18 times that of the transmitted signal. So the echo signal is very, very weak. But still we need to detect that echo signal in the presence of noise. So we use a low noise RF amplifier. Best example is parametric amplifiers. Parametric amplifiers do not involve any resistors. Probably you might have studied about thermal noise, etc. Most of the noise is basically added because of the resistive component. So if you can design an amplifier without involving a resistor, the noise will be eliminated automatically. So that is actually best example is parametric amplifiers, okay, which make use of only the capacitors for amplification. Next, the conventional superhet receiver. So that RF signal will be converted into IF signal by using local oscillator and mixer. So here you get IF signal, and most of the amplification is done by IF amplifier. IF amplifier is also known as a matched filter. The reason for this one is we designed the IF amplifier. Okay, for example, HF is the response to the IF amplifier. Okay, a signal is, let us say, SF. I am representing a signal as SF, and the response, frequency response of IF amplifier is, let us say, HF. Magnitude of HF should be equal to magnitude of SF. Similarly, phase of HF must be opposite to the phase of SF. Okay, so if you can, of course, I don't want to go into details. It is also given in Skolnick. Okay, so if you can design the IF amplifier in such a way that, okay, magnitude of HF is equal to magnitude of SF, phase of HF is opposite to the phase of SF, then we can maximize the peak signal to mean noise ratio. Okay, that IF amplifier so designed is going to maximize the peak signal to mean noise ratio. Okay, then the second detector. Ultimately, we want basically envelope, or you can call it as a baseband signal. This is basically the envelope, you can say that. Okay, second detector, and that can be displayed on a display. Okay, it can be A scope display or PPA display or any other display, B scope display. Okay, after sufficiently amplifying the signal using video amplifier. Okay, for example, this is the typical signal. You can call it as a baseband signal. Okay, or you can call it as a one sweep, which I've told you. This is let us say at this instant of time a pulse is transmitted, and at this instant of time I am transmitting the second pulse. So this is the signal that I have received before transmission of the second pulse. We call it as a sweep. You can very clearly see that a target, wherever there is a target is there, the amplitude is more. Okay, and rest of the things can be treated as a noise signal. Next. Now, how do you say that there is a target? Okay, how do you differentiate between the target and noise signal? Okay, the previous case actually, you can see that wherever there is a target, the amplitude is more. The rest of the things are taken as a noise. Who is going to judge? On what basis I can say that this is a signal that is coming from a particular target? The rest of the things are going to be noise signals. So what we do is we adopt threshold detection. So what we do is we set up a threshold level. Okay, at the receiver end, we set up a threshold level. We say that whenever the strength of the echo signal exceeds the threshold level, say that there is a target. Okay, suppose if the signal strength, echo signal strength is less than the threshold level, we assume that it is a noise signal. Okay, for example, so this is the threshold level. I've kept the threshold level here, and even setting up a threshold level is also a complicated thing. For example, as it is, if you look at this diagram, I've kept the threshold level here, and I'm looking for three targets: target A, target B, target C. I'm looking for three targets. Suppose if I keep the threshold level slightly high, like in the diagram, because the echo pulse that is coming from target A is able to exceed the threshold level, so certainly target A gets detected. Target B just gets detected because it is just able to overcome the threshold level. What about target C? The echo signal that is coming from target C is less than the threshold level. So we are going to miss out this particular target. I hope you are understanding. Okay. How to set up the threshold level is going to be a difficult task. Suppose if I keep the threshold level too high, there is every possibility that I'm going to miss out a few potential targets. Like in this example, I'm missing out the targets here. Suppose if I keep the threshold level too low, okay, too low, then what happens? Apart from the potential targets A, B, and C, there is a possibility that noise alone will be able to overcome. For example, if I keep the threshold level here, okay, this is a noise signal. Noise alone will be able to overcome the threshold level. Then what happens? Even though there is there is no potential target, because noise is able to overcome the threshold level, able to exceed the level of the threshold. So we assume that there is a target. That target is known as a false target. Okay, even though there is no target, because noise is able to overcome the threshold level, we assume that there is a target. Okay, we call this as the false target. This condition is known as false alarm condition. What is a false alarm condition? Suppose if I keep the threshold level too low, there is every possibility that noise alone will be able to overcome the threshold level. Okay, so we assume that there is a potential target, even though there is no target. That particular target is known as a false target. This condition is known as a false alarm condition. So we need to go via media. Suppose if I keep the threshold level too high, there is a very possibility that some potential targets will be missed out. And if I keep the threshold level too low, what is the problem? Apart from the desired target, there is a possibility of occurrence of these false targets. Okay. Then how you are going to design? Once again, it all depends upon the application point of view. In fact, if you read the Skolnick thoroughly, he has given very beautifully. Sometimes actually, our intention is I should not miss out any any potential targets. I want all the three targets A, B, C, okay, to be detected. In the process, I am not supposed to miss out any potential targets. Then I can keep the threshold level slightly low, so that all the three potential targets A, B, C will be detected. Okay, in the process, you may get some false targets also. No problem. That's actually my intention is not to miss out any potential target. Sometimes actually the requirement is I should not get any false target. Then I have to keep the threshold level slightly high. So it all depends upon the application. This is basically so far we discussed about the pulse radar. Any questions you got on the pulse radar? Any questions? That range equation, do you want me to explain? It is a simple equation. This is, of course, one of the important derivations, radar range equation. Power density. So I'm not going to discuss about this. It's a very simple equation. Okay. Let me go to CW radar. We have covered almost all this one. Try to understand the examples which I have given, okay, so that you can understand in a better way. On CW radar, by using a pulse radar, we can measure the range of the target. Certainly, we can say that it is at a height of, let us say, it is at a distance of 100 kilometers or 50 kilometers. Precisely, we can determine the range of the target. But sometimes, actually, apart from the range, we also need the velocity with which it is traveling. It is something like, suppose, when you are looking for an aircraft, okay, in tracking radar, you're going to get all these things. You want at what height the aircraft is traveling, with what velocity it is traveling, in which direction it is traveling. So apart from the range, we also need with what velocity the object is traveling. Similarly, you are tracking a missile. Certainly, we need with what velocity it is traveling. Okay, but by using a pulse radar, it is not possible to measure the velocity of the target. Only the range can be obtained. By using a CW radar, velocity of the relative velocity of the target can be obtained. You know what is the relative velocity and what is the velocity? What is the difference between the relative velocity and velocity?
Velocity is like the actual,
Actual velocity.
yeah, speed, distance by time, displacement by time, but relative velocity is with respect to two, like, for
So,
example, yes, trains like that.
yeah, two
Moving,
trains traveling in opposite directions.
yes.
Velocities get added. Okay. Now this continuous wave radar in fact works on this Doppler principle. In sound, basically, you might have studied about this Doppler principle. If either the source of oscillation or the observer of oscillation is a motion, then there will be apparent shift in frequency that results in. That is basically a Doppler principle. So here, uh, for example, you got a speeding vehicle. Okay, F naught is the frequency with which we are transmitting a signal. It is a continuous wave. It is not in the form of pulses. The signal will be transmitted continuously towards a target. Okay. Suppose if the target is traveling towards the radar, we call it as approaching target. Approaching target means suppose if the target is traveling towards the radar, as time passes, what happens? The distance between the radar and the target gets decreased. It is approaching target. It is something like you are in fact standing at a point stationary, and a car is traveling, approaching you. What happens as time progresses? The distance between you and the car decreases with respect to time. We call it as approaching. Okay. Once it crosses, once the car crosses you, and it goes in the other direction. So what happens? It is a receding target. As time progresses, what happens? The distance between you and the target increases with respect to time. That is a receding target. Okay. So approaching target means as time progresses, the range or the distance between the radar and the target decreases with respect to time. Receding target means, okay, exactly in the opposite direction. So now, suppose you are transmitting a continuous wave, a fixed frequency towards the target. That signal once again gets intercepted by the target. Part of the signal will be reflecting back. The reflected signal will have a different frequency from the transmitted frequency. If it is an approaching target, it will be F naught plus FD. If it is a receding target, it is F naught minus FD. So what we do is we combine these two signals, F naught and then the received signal, F naught plus FD or F naught minus FD. What is the difference frequency FD? We call it as a Doppler frequency. Once we measure the Doppler frequency, okay, we can determine the velocity of the target. So that is a simple principle. For example, let us say the distance between the radar and a moving target is, let us say, R. Okay. R is, of course, is the function of time. R is not going to be constant. If it is a approaching target, R decreases with respect to time. If it is a receding target, naturally R increases with respect to time. Okay. So once again, the signal, the continuous wave signal, which is transmitted, let us say at time t is equal to 0, has to go to the target, and then there it gets intercepted by the target and reflects back to be detected by the radar. How much time it takes? 2r by c seconds. Once again, the signal travels with the same velocity of c, right velocity. So the total distance it covers is 2r. So 2r by c is the time taken for the signal to go to the target and then back to the radar. How much distance it is traveling? R plus R, 2r. R plus R, 2r. The 2r, if you represent in terms of lambdas, how many wavelengths it has traveled? It is something like, suppose it has traveled a total distance of, let us say, 100 meters. Only as an example, I am telling 100 meters. 50 meters plus 50 meters, 100 meters. Suppose the value of lambda is c by f naught. Suppose lambda is 10 meters. The distance of 100 meters, lambda is 10 meters. How many wavelengths it has traveled? 10 lambdas it has traveled. Have you understood? Okay. That 100 meters, if you represent in terms of lambdas, each lambda means 10 meters. How many lambdas it has traveled? 10 lambdas. Okay. So, in the expression, how do you find this? 2r by lambda, so many wavelengths it has traveled. 2r by lambda. I've understood this. 2r by lambda, so many wavelengths. Each wavelength, suppose when the signal travels a distance of 1 lambda, how much phase excursion it makes? How much phase excursion it makes? So here I have given, okay, 2r by lambda. Each wavelength means 2 pi radians. So what is the total phase shift undergone by the wave during its to and fro transmission? 4 pi r by lambda. Have you understood this particular value, how it has come? Because this is going to, in fact, you are going to get this number of times. Have you understood? For example, you have got a target located at a distance of r meters. That means it is nothing but the distance from the radar to a particular target. Now you are transmitting the signals continuously. The signal is continuous. But whatever may be the signal has to go to the target after covering a distance of r. There it gets intercepted by the target, and then a part of the signal will be reflecting back. Once again, it covers a distance of r during its fro transmission. So during its to and fro transmission, a total distance of 2r is covered. That 2r can be represented in terms of lambda, how many wavelengths it has covered. Because we are transmitting the signal at a constant frequency of f naught, you can find out what is lambda. Lambda is equal to c by f naught. Okay. So the 2r, how many wavelengths it has traveled? 2r by lambda, just like 100 meters. Okay. Suppose if the wavelength is, let us say, 5 meters in this case. How many wavelengths it has traveled? 20 wavelengths it has traveled. Suppose if the wavelength is 10 meters, the same distance of 100 meters, in terms of lambdas, 10 lambdas it has traveled. Okay. So 2r by lambda, so many wavelengths it has traveled. What is basically a wavelength? When the wave travels a distance of lambda, what is the phase excursion it undergoes? 2 pi radians. So what is the total phase shift undergone by the wave during its to and fro transmission? 2r by lambda, so many wavelengths, and each lambda 2 pi radians. So 4 pi r by lambda. So let me call this as phi. Okay. Now here r is not constant. As I already told you, suppose if it is a receding target, r increases with respect to time. If it is approaching target, r decreases with respect to time. So if I differentiate this with respect to time, d phi by dt, d phi by dt is equal to 4 pi by lambda into dr by dt. Okay. So d phi by dt is nothing but angular frequency omega d. What is dr by dt? R is the distance, change of distance with respect to time. It is nothing but the velocity. So dr by dt is nothing but the velocity. So 4 pi by lambda into Vr is equal to omega d. What is omega d? 2 pi into Fd. So you can find out Fd. Fd is equal to 2 Vr by lambda. So if you look at this one, once we measure this FD, what is FD? The Doppler shift undergone by the wave. So you are transmitting a signal at a frequency of F0. The echo signal will have a different frequency, either F0 plus FD or F0 minus FD. So once you mix the echo signal, which has a frequency of F0 plus or minus FD, with the transmitted signal, which has a frequency of F0, then you get the difference frequency FD. Once you get the difference frequency FD, okay, FD is measured 2 VR by lambda. What is unknown quantity? VR. VR is a velocity. That's how actually velocity of the target can be measured. Okay. Next. What is lambda? Lambda is equal to C by F0. So the same thing I have written here, C by F0. So FD is proportional to F0. Doppler frequency is directly proportional to the transmitted frequency. That means if you operate the radar at, let us say, with a frequency of 2 megahertz, you get one Doppler frequency. If you operate the in fact CW radar with a frequency of 10 megahertz, if F0 is increased, naturally FD also will be increased. So there is a direct proportionality between FD and F0. Okay. So as an example, CW radar transmit frequency of 5 gigahertz. So F0 is 5 gigahertz. Calculate the Doppler frequency by seen by a stationary radar. Okay. When the target is radial velocity of 100 kilometers per hour. The lambda you can find out 6 centimeters. FD is 2 VR by lambda. So 2 into VR is given. So one thing that we have to note down is 100 kilometers per hour. The velocity is given as 100 kilometers per hour. You always have to represent this velocity in meters per second. Okay. ఏం చేస్తారు దానికి కన్వర్షన్ 100 kilometers per hour divided by 3.6, then you get in meters per second. That is equal to 27.7 meters per second. Remember this. Okay. Like that, of course. Now this is the simple block diagram of a CW radar. In fact, as the diagram clearly explains, so you have a transmitter, okay, which generates a continuous wave signal of frequency of F0. So this signal will be radiated towards the target. What is the frequency of F0? So if there is, this target has got a relative velocity with respect to radar, naturally the echo signal will have a different frequency of F0 plus or minus FD. Okay. So what I'm going to do is I'm going to combine this transmitted signal having a frequency of F0, and then the echo signal is having a frequency of F0 plus or minus FD. So when you mix these two signals, okay, you get the difference frequency in a detector. Okay, difference frequency is FD. Okay, so this FD, normally the value of Doppler frequency is very, very small. The maximum frequency will be only 1 kilohertz or at the most 10 kilohertz. Mostly it is going to be in hertz. So Doppler signal is a very low frequency signal. So that low frequency signal needs to be amplified using a low frequency amplifier, because it is a bit frequency amplifier, or in some cases it is given as a Doppler frequency amplifier. Basically it is a low frequency amplifier. And it is given to an indicator. What is this indicator? So if you just want to determine whether there is a moving target or not, okay, this indicator can be just earphones, pair of earphones. Okay, but if you want to determine what is the velocity, what is the exact velocity, that means if you want to find out VR, then this indicator must be a frequency counter. Once it is a frequency counter, you can measure what is FD. Once you measure FD, okay, FD is equal to 2 VR by lambda. Using that equation, you can find out the relative velocity. Okay, it all depends upon whether you really want to measure the velocity or just you want to find out whether there is a moving target or not. Okay. Suppose if there is a target, the target is stationary. The target is stationary. What will happen to this? What is the frequency of the echo signal? Fd is equal to 2 VR by lambda. If the target is stationary, what is VR? 0. What is Fd? 0. So what is the frequency of the echo signal? F0. What is the transmitted frequency? F0. So what is the difference frequency? 0. That means you get a DC signal. Okay. So we get a DC signal. And the beat frequency amplifier that we are going to design is not supposed to amplify the DC signal. DC signal corresponds to the stationary target. When we are looking for a target which is moving with certain velocity, and when we are trying to find out what is the velocity of that, is it not? We need to eliminate these stationary targets. So the beat frequency amplifier has to be designed, the frequency response has to be in such a way that it is not supposed to offer any gain for DC signals, for stationary targets. Okay, and it is supposed to offer gain. It is supposed to amplify the signals that are coming from moving targets. I hope you have understood this particular point. Okay. But normally this is not the block diagram that is used, because this is called homodyne receiver or superhet receiver with the 0 IF. Because amplification is done entirely by one amplifier, beat frequency amplifier. That the amplification is done for Doppler signal, a low frequency signal. There is one noise which is known as a flicker noise. Flicker noise is indirectly proportional to frequency. That means at low frequencies, the effect of flicker noise is very high. Okay, so when you try to amplify the signal, okay, a low frequency signal by using a beat frequency amplifier, the effect of flicker noise is going to be very severe. So what we need to do is we need to amplify the signal at IF stage by using IF amplifier. This is basically non-zero IF receiver. Okay, the superhet receiver. See the difference between this practical circuit and the one which was discussed previously is here most of the amplification is done by the IF amplifier. Okay. Thereby, the impact of flicker noise, the effect of flicker noise can be reduced. So here also F0, the transmitted frequency is F0, okay, and the echo signal frequency is F0 plus or minus Fd. Earlier, what we have done, we have mixed these two signals directly. We got a Doppler frequency that we have amplified directly. Because of that, flicker noise has come into picture. So to eliminate the impact of the flicker noise, what we do is, so I'm locally generating an IF signal. Okay, that IF signal is mixed with F0. So F0 and FIF. When these two are given to a mixer, you know what is the output of the mixer? Individual frequencies F0, FIF, upper sideband F0 plus FIF, and the lower sideband F0 minus IF. We can select either the upper sideband F0 plus IF or F0 minus IF by using a sideband filter. So here this selects only the upper sideband F0 plus FIF. So now this is the signal. This signal will be mixed with the echo signal, which is at a frequency of F0 plus or minus Fd. What happens? F0 will be cancelled. So FIF plus or minus Fd. FIF plus or minus Fd. So FIF will be approximately, let us say, 1 megahertz. Suppose if the transmitted frequency is 100 megahertz, FIF will be, let us say, 1 megahertz. Only in an example I am telling. Okay, Fd will be few hertz. So FIF plus or minus Fd will be almost at IF frequency. 1 megahertz plus 50 megahertz is almost IF frequency. So that signal will be amplified by the IF amplifier. And most of the amplification is done by this IF amplifier, so that the impact of the flicker noise can be reduced. Okay. And then the second detector, what we do is this FIF, this oscillator signal will be given as one of the inputs to the second detector. Okay. So FIF is one input, FIF plus or minus FD is another input. We get the difference frequency FD. So once again, the beat frequency amplifier, Doppler amplifier, and then indicator. Okay. So this is what we do practically. Okay. Direction of course. And probably you might have understood one particular point. Let us go back here. When we mix these two signals, the echo signal having a frequency of F0 plus or minus FD and the transmitted frequency of F0, we get the difference frequency. Even if the frequency is F0 plus FD for the approaching target or F0 minus FD receding target, the result is same, the difference frequency is FD. So once we measure FD, we can find out only the relative velocity, but we are not sure whether it is an approaching target or a receding target. If it is plus FD, okay, then we can say that it is an approaching target. If it is minus FD, then we can say that it is a receding target. Unfortunately, the sign of the Doppler frequency, plus FD or minus FD, that sign we are missing here. So once we are not able to measure the sign, we are not able to, we will not be able to determine whether it is an approaching target or a receding target. So for that, of course, there is a mechanism. Basically, the signal is given to two mixers depending upon the rotation of the synchronous motor. If it rotates in the clockwise, we say that it is an approaching target. If it rotates in the anti-clockwise direction, it is a receding target. Okay. Anyway, we don't have time to discuss that because I'm more concentrating. I should concentrate on the FMCW radar. What is the drawback of a simple CW radar? Obviously, range can't be measured. Is it not? So it is not possible to measure the time taken for the pulse or for the signal, continuous wave signal, to go to the target and then back to the radar. The reason is simple. We are transmitting the signal continuously and we are receiving the signal continuously. So as such, we're not able to measure the time taken. But in the case of pulse radar, the transmission is discontinuous. Only at time t is equal to 0, a pulse is transmitted. So naturally, whatever echo signal that we receive, we are very sure that that echo signal is received due to the pulse that is transmitted earlier. So we are able to measure the time. But here it is not possible to measure the TR, time taken for the signal. Okay, it is something like suppose you just want to find out how much time people are spending in a temple. People are going inside the temple, spending some time and then coming back. Okay, so you want to find out what is the average time a person is spending inside the temple. Suppose all people wear white dress, okay, an influx of visitors, thousands of people wearing white dress, they are going inside and then coming back, returning back. Is it possible to identify? No, it is not possible. Suppose you ask one person to wear a black dress, okay, another person yellow dress, another person red dress, okay. Now rest of the people, of course, let us say they are wearing white dress. So once the person with black dress is entering, okay, at what time he is going inside the temple and what time he is coming back, you can find out how much time he is spending. Similarly, how much time a person wearing red dress is spending time. So find out, you can add. So you are able to find out, okay, at what time you are transmitting the signal, okay, and if you are able to find out at what time you are receiving the signal, then you can find out the value of TR. But unfortunately, here it is not possible. So that is one of the main drawbacks of CW radar. Range can't be measured. Okay. So in the case of FM CW radar, what we do is instead of transmitting the signal continuously at a constant frequency of F0, okay, the frequency is varied in a known fashion. The frequency is varied in a known fashion. Let me straight away explain this with an example. So frequency modulated CWR. Now, for example, I am increasing the frequency continuously. Okay, linearly I am increasing. So as time progresses, at this time, this is the frequency. This is the starting frequency, that is 100 megahertz. As time progresses, I am increasing the frequency. Okay. Okay. Then this allows us to determine the range. Let me tell you how it can be obtained. For example, at time t is equal to 0, the frequency of the signal that is transmitted is 100 megahertz. I am increasing the frequency continuously. For every 1 millisecond, I am increasing the frequency by 10 megahertz. At time t is equal to 1 millisecond, what is the frequency I am transmitting? 110. 2 milliseconds, 120. 3 milliseconds, 130. Like that, 5 milliseconds, 150. 9 milliseconds, 190. 10 milliseconds, 200. Now I am increasing the frequency. I am not transmitting the signal at a constant frequency. I am transmitting the signal, okay, at with increasing frequency. Okay. For example, a signal is taking a time of 1 millisecond to go to the target and then back to the radar. Try to understand this particular point. Okay. The signal that we are transmitting at time t is equal to 0. What is the frequency of the signal, transmitting signal? 100 megahertz. So this 100 megahertz of signal, okay, which is transmitted at time t is equal to 0, has to go to the target and then has to return back. It takes a time of 1 millisecond. So at what time I am receiving this echo signal of 100 megahertz? 1 millisecond. Have you understood this particular point? Similarly, at time t is equal to 1 millisecond, I am transmitting 110 megahertz of signal. So this also has to go to the target and then back to the radar. It also takes the same time interval of 1 millisecond. So at what time I will be receiving the corresponding echo signal? Time t is equal to 2 milliseconds. Okay. So what you have to do is, at any instant of time, if you find out what is the difference in frequency, what is the frequency of this echo signal and the frequency of the transmitted signal at that instant of time. 110 minus 100, it is 10. 120 minus 110, it is 10. So this 10 megahertz. This 10 megahertz gives you at what range it is the target is there. For example, suppose if the range is increased, okay, right now the target is located at some range, let us say R1. So for that, the signal is taking 1 milliseconds time to go to the target and then back to the radar. Now suppose if the range is increased, what happens to the time taken for the signal? Will it be increased or not? Suppose if the range is increased, naturally the time taken for the signal to go to the target and then back to the radar, it takes more time because the range is increased. Instead of taking 1 millisecond, let us say now the signal takes a time of 2 milliseconds to go to the target and then back to the radar. So at time t is equal to 0 milliseconds, I am transmitting 100 megahertz of signal. At what time I am going to receive the corresponding echo signal? 2 milliseconds. Suppose if the range is increased because it's taking a time of 2 milliseconds. So here it becomes 100. 120 minus 100. Now the difference in frequency is 20 megahertz. Earlier it is 10. Now it is 20. Why there is an increasing difference of frequency? Because the range is increased. So what you need to understand is the difference in frequency, we call it as a beat frequency. The beat frequency, earlier it was 10 megahertz. Now we have increased the range. Now it has become 20 megahertz. The beat frequency is proportional to the range. So this suggests that once you measure the beat frequency, we can find out the range. Okay. Okay. Now the problem with this one is, see, we can't keep on increasing the frequency. We have started with 100 megahertz, 200 megahertz, 300 megahertz, 500, hundreds of gigahertz. After that, what happens? So frequency can't be increased continuously. Some periodicity must be there. Okay. For example, I'm changing the frequency in a triangular fashion. If you want, we can change the frequency in the form of a sawtooth. Okay, whatever you want. Now here what happens, I am starting from 100. Let us say it is going to a maximum of 150 megahertz. After that is once again 100, then 100 to 50 megahertz. Then 50 to once again it is increasing. So like that, it lies between a minimum frequency of 50 megahertz to a maximum frequency of 150 megahertz. For example, here, this particular frequency, let me give you this example. Now I'm changing the frequency in the triangular fashion. We call this as a modulating signal. Okay. Now the modulating signal is triangle. 100, 110, 120, 130, 140, 150. So it has reached the maximum frequency of 150. After that, I'm decreasing the frequency 140, 130, 120, 100, 100. Then afterwards 90, 80 like that it will be decreasing. Okay. Now let us see what happens. The signal, for example, at the same range, okay, it is taking a total time of 1 millisecond to go to the target and then back to the radar. The signal that we have transmitted at time t is equal to 0 of 100 megahertz, okay, takes the time of 1 millisecond to go to the target and then back to the radar. So at what point of time I will be receiving the echo signal? At time t is equal to 1 millisecond, this is the echo signal. Okay, then 110. Now, if you find out the difference, 110 minus 100, 10 megahertz, 120 minus 110, 10 megahertz. Okay, so we are able to get this bit frequency is 10 megahertz, which is directly proportional to the range as we have discussed. Okay. So now, this is basically here FB is 10 megahertz. At this instant of time, the bit frequency is 0. Here you can see that this is a transmitted frequency. This is the echo signal frequency. Exactly at this instant of time, the transmitted frequency is exactly equal to the echo signal frequency, so that the bit frequency is 0. So now in this example, can you please tell me at what time the echo signal frequency and the transmitted frequency will be equal so that the bit frequency will be 0? Hmm? 140, 150, now it is decreasing. So exactly at 5.5 milliseconds, what is the transmitted frequency? Can you please tell me? 145. At 5 milliseconds, 150. 6 milliseconds, 140. 5.5, 145. Now, if you look at the echo signal frequency, 140 and then 145, 150. So exactly at 5.5 milliseconds, the transmitted frequency is 145. The echo signal frequency is also 145. That's why you are getting this 0 here. Okay, similar is 0 here. But anyway, what we want is the bit frequency. Once you measure this as 10 megahertz, we can find out the bit frequency. From that bit frequency, I'm giving this equation directly. Once you measure this bit frequency FB, you can determine the range. Okay. What is FM? Modulating frequency. Okay. This is modulating frequency. So here what we do is, so I'm changing the frequency in the form of a triangle. So this is 50 megahertz, this is 150 megahertz. So let me represent this as delta F. Delta F is a changing frequency. So this delta F, change in frequency of delta F is obtained in a span of Tm by 2. Tm is the period of time for the modulating signal, Tm. So Tm by 2, the frequency is changed to delta F. So what is F naught dot? change in frequency delta f within a span of half the period of modulating signal Tm by 2. So 2 delta f into f. That of course I've incorporated here, so you can find out the range. Now finally, this is the last point I would like to discuss. Suppose if the target is stationary, okay, we can find out. Suppose if the target is a moving target, then the Doppler shift also gets added. Suppose if the Doppler shift is, let us say, 1 megahertz, okay, the Doppler shift. Suppose if the target is an approaching target f0 plus fd, if it is a receding target f0 minus fd, that fd, assume that it is a 1 megahertz. Okay, so what happens? Same 0 milliseconds, 100, 110, 120, 130. Once again, it is decreasing like okay, with this transparent signal. Now, suppose if the target is approaching target, then this becomes 100 plus fd. Okay, because it is an approaching target. That fd, let us say 1 megahertz. So what happens? Echo signal frequency will be 101. So here, echo signal frequency will be 110 plus 1 megahertz, 1 level like that. Okay. So what happens if you find out the difference frequency? Okay, 110 minus 101, it is 9. 120 minus 111, it is 9. Like that, 9999, this is 1111. Okay. So if you carefully look at this one, FR is 10 megahertz. Okay. FD is 1 megahertz. If you have the value of FD, you can find out the velocity of the target. If you have the value of FR, you can find out the range of the target. Okay. So from this, how do you find FR and FD? You can see that what is 10 minus 1? It is 9. What is 10 plus 1? It is 11. So during the increasing part of the modulating signal, we get FR minus FD. During the decreasing part of this, we get FR plus FD. So what we do is, here, we use basically two counters, average counter and then a fixed frequency counter. That switched frequency counter gives us FD, the average frequency counter gives us FR. So here you can see that during the increasing part of the modulating signal, you get FR minus FD. That is basically 10 minus 1, it is 9. During the decreasing part, we get FR plus FD, that is 11. Okay. So suppose if I take the average of these two, FR plus FD plus FR minus FD by 2, then you get FR. That means you get the range. Suppose if I take the average of the difference, FR plus FD minus of FR minus FD by 2, then you get FD. Once you get FD, you can determine the relative velocity of the target. So this is basically what is done. So once we get the signal here, we use two counters, switched frequency counter, okay, which gives us the average of the difference of these two frequencies. That means 11 minus 9 by 2, we get the Doppler frequency of D. So because of that, we can find out the Doppler velocity. And then average frequency counter, FR plus FD plus FR minus FD by 2. So you get FR, that means you get 10 megahertz. From that, you can find out the range. Okay. So I think I can conclude here. So you have any specific questions? I'll try to answer. Any specific questions you have?
Students, if you have any doubts, you can raise.
Yes, Aparna, I think. Tulasi,
Yes, sir. I was about to ask you about the question Aparna ma'am put in chat box.
what is the chart box? I have not seen that. Please read that.
What can be the minimum and maximum value of FD, sir?
What can be the minimum value of the FD, Doppler frequency?
Yes, sir.
It all depends upon the target which you are looking for. So a few heads to normally a few kilohertz. See, the design of the Doppler frequency has to be done in such a way that, see, for what target actually you're looking for, what is the approximate velocity it is traveling, then what is the approximate value of FD it gives us. Okay, accordingly. And before I conclude, I just want to show you one thing. This is basically right. See, right now, these are the flights that are moving. You can see how many flights are there. And in fact, if you amplify this picture, you can also see that it is really moving. Let me concentrate on one particular flight. Can you see this? This is moving. Is it visible? Or let me amplify further.
Yes, sir, it is moving.
Yeah, this is. Now you can see that it is moving. Okay. Now, once an aircraft leaves from the airport, okay, and before it reaches the destination point, the tracking radar basically gives a continuous information, something like, let me show you. For example, uh, British Airways BA 2726. BA 2726. There is one flight is there. Yes. Because it is already arrived. Yeah. This is basically from Hyderabad to already reached. I am just replaying this one. See how. Let us 10x speed. 50x. Okay. Now, once it takes off from Hyderabad Rajiv Gandhi Airport, and how it is traveling, this you can see. Okay. Okay. Then let me show you view track log. In fact, so now this is the information. Okay. It has departed from Hyderabad at 7:59 13 seconds IST. Okay. 13:30 54 So almost for every 10 to 20 seconds, it is providing information, latitude. Okay, that is nothing but what is latitude and what is longitude between theta and phi. Similarly, with what velocity it is traveling, miles per hour. Okay. Similarly, this meters is the range, nothing but at what height it is traveling. So initially 802 meters, 992. So it has reached 2,927 meters. Okay. 3 kilometers, 4 kilometers, 5 kilometers, 6 kilometers. So maximum like this. Okay. 10,782 meters. Okay. So at what height it is traveling? These are nothing but theta and phi. So direction, which direction it is traveling? Okay. With what velocity it is traveling? So this is what is known as a tracking radar. Tracking radar means any radar that supplies a continuous information on a particular target. That continuous information can be a range information, can be the value of theta, can be value of phi, can be the value of velocity. So that is known as a tracking radar. Okay.
Yeah. Tulasi?
Yes, sir.
Yeah. Can you propose the vote of thanks?
Yes, sir. 1 second, sir. I would like to now propose vote of thanks. I take this privilege to propose vote of thanks on behalf of Signal Processing Society, IEEE GZSP. I express my sincere gratitude to Professor B. Harikumar sir for delivering a profound lecture on fundamentals of radar signal processing. Thank you, sir. I thank Dr. P. Sudhakar sir for his guidance and help in organizing this event. I thank my event coordinators and GSET for making this event possible. Thank you everyone for joining and making this event a great, grand success.
Okay. Thank you. Thank you all.
Thank you, sir. Everyone can lead the meet.
Thank you.